Morning, guys. I'm here with Frankie today to talk about something that a lot of people think about. Some people don't think about it. Why electric bikes have difficulty getting traction at low speeds. Takes me back to an article I read by Kevin Cameron. He was the tech editor for Cycle World magazine for years, and every month when Cycle World would come out, he would write a pretty interesting article about some technical thing that had to do with motorcycles. He wrote an article about why single cylinders and twin cylinders are used exclusively off-road. Occasionally at triple, like the Triumph Tiger, but that's more of an ADV. As far as a true off-road bike, you're looking at mostly singles, maybe the occasional twin. And the reason is the power pulses the engine puts to the rear wheel. The simple answer is power pulses. Power pulses are the way the engine delivers its power to the rear wheel. And an electric motor doesn't produce power pulses like an internal combustion engine. It produces constant power. In a nutshell, you can think of it like anti-lock brakes in reverse. ABS brakes work by when you lock up the rear brakes, the sensor senses that, cuts brake pressure to the rear wheels just for an instant and allows the tire to start rolling again. And when your tire is rolling, that's when you have traction, right? When your tire is sliding, you don't have traction. So that brings me to another topic of this video is basic physics principle is rolling friction versus static friction versus sliding friction. Now, when a tire or any object resting on the ground or a surface, when that object is at rest, it's experiencing static friction, and that's the object's resistance to movement from a force in any one direction. Sliding friction is once you have that object in motion against a surface. Sliding friction is the force trying to bring the object back to rest.
An example of how sliding friction and static friction are different. This block is being held up here on this ramp because of static friction. There's actually friction between the two boards that allow it to stay there. If I just give that block a little tap, it's going to turn into sliding friction. And notice, so it just kept going. And why did it keep going is because sliding friction is actually less than static friction.
Rolling friction is when you have a wheel or really anything rolling, something round, that wheel or object is going to want to come to rest eventually. Once a tire breaks traction, moves from rolling friction into sliding friction, the coefficient is a lot less, which means it's harder to get traction. Static friction, rolling friction, and sliding friction all have coefficients. Static friction will be the greatest. Sliding friction is always less than static friction, and rolling friction is really a combination of the two, but also minimal. One video I watched recently that really illustrates my point in this video was Kyle Brotherson of Dirt Bike Channel. I've been watching him for years. He's an awesome rider. He's got thousands of hours of experience on mostly two-stroke dirt bikes, a lot of other motorcycles as well. Kyle, if you're watching this, I've been a longtime fan. Got my Dirt Bike Channel sweater on, got my t-shirt on underneath, got my socks on. Still trying to win that dirt bike, man, so I'll keep my fingers crossed. So hopefully you don't mind I poached part of your video to illustrate my point in this video. Anyway, over the summer he had an electric dirt bike called a Stark Varg, and he was on a trail trying to ascent a mountain, and it was a loose, rocky, uphill single track where the going is really slow and you need to hunt for traction no matter what you're riding in order to continue up the trail.
So I'm going to fast forward this a little bit. Guys, I'm trying not to dig up the trail here because this is the trail I know and love, and I'm trying not to just dig the thing out. So I've taken probably 8 or 9 different models of bikes up this thing, everything from KTM XCs and XCWs and gases and Shercos and Beta and TM and all of these different bikes up this exact trail. And it's a loose, nasty, rocky section of trail. There's nothing fun about this particular section, these set of switchbacks. but I've never seen a bike, like all the way, even getting up to here, I've never seen a bike struggle for traction quite like this one. Now, I'm running tubeless at a lower pressure, but I'm running a Dunlop AT81. It's not like one of my gummy tires, but this bike struggled worse than any bike I've ever had. Even getting up to this point, I just could not get any traction at all. It was insane.
And he was struggling and struggling, and he was saying in the video how difficult it was to get the thing to find and maintain traction, especially compared to his two-strokes motorcycles that he'd been up there countless times in. And he also said in his review he didn't really know why that was. He understood, tires have a lot to do with it, bike setup has a lot to do with it. Anyway, this is why. Frankie's a 4-stroke engine, 500cc single. Every time that one of the 4 strokes, power stroke, when the engine fires, that's delivering torque through the transmission, through the clutch, down the chain to the sprocket to the rear wheel, and ultimately it puts the torque right here, right where the tire is making contact with the ground, right? Propelling you forward. So if you think about it, as you're rolling forward and the engine is running, the engine is only producing a pulse of torque to that rear wheel every so often. That pulse of power is timed with the engine depending on speed, depending on what gear you're in. The pulse of power to the rear wheel is not constant. It's intermittent. In reality, say you're in first gear hypothetically, and your takeoff RPM from a stop is 3,000, and you dump the clutch or you slip the clutch trying to hunt for traction to start a hill climb. Say you're on a hill. Those power pulses, I did the math, and they're really like a quarter of a degree apart on the wheel, based on, say 2.5 gear ratio in first gear, 52 or 53 to 13 sprocket ratio. So gear ratios have a lot to do with this, of how far those power pulses are spread apart.
Anyway, it's relatively steep. I would say probably a 25 degree incline. This is a perfect example of where an electric bike would have a lot of difficulty getting going from a stop on an uphill where traction is limited. So let's see how a low geared 4-stroke does. Here we go. See, it's starting to slide, but you can modulate the clutch, keep her going. Once you've found traction, maintain momentum. And up we go. Woo!
We're going to pretend for illustration's sake that this spare front tire I have here is the rear wheel of the motorcycle. So this is an extremely exaggerated example of how this works. Just bear with me, and for example's sake, let's say that the engine is delivering power pulses every quarter turn of the rear wheel. From here to here is 720 degrees of the engine. So the engine fires here, fires. So that means that every time the rear wheel hits one of these spots to the ground, that's when the rear wheel has the opportunity to break traction. That's when the power can overcome the static friction and rolling friction between the tire and the ground. That's when the torque burst will occur to the tire. Everything in between here, from dot to dot, there's nothing happening. There's no power being delivered to the tire. It's just rolling. Also, the engine, I don't know if you guys have ever tried to kickstart a large displacement engine like this 500, for example. It's pretty difficult to kick, and that resistance to the Kickstarter is from the compression of the piston moving up. Also, the valve train, those springs are pretty tough, so they offer quite a bit of resistance. So that means during this time from here to here, the engine is actually trying to slow down the tire during this coast period. And then it fires again and overcomes that and and you continue on. Now, one thing engineers and companies do to try to compensate for the resistance the engine is giving you during this time is they'll add a flywheel weight that gives the flywheel spinning inertia and momentum to help carry it through to the next power cycle. So let's call this a 4-stroke single cylinder engine delivering power every quarter turn of the tire. So what happens when you have a twin cylinder? In the old days, almost all twins had 180-degree crankshafts. That means of the two pistons, they're either firing in opposite, opposed to each other like this, or they're coming up together, and each one is firing every other time. So you get 180 degrees between power pulses to the rear wheel, which would look like this. So now you have twice the number of opportunities in rolling time for that tire to break traction. And once traction is broken, since sliding friction is less than static friction, it's more difficult to regain that traction. This illustrates a twin cylinder 180 degree firing order. So one thing a lot of companies started doing in modern times with twin cylinder engines is installing a 270 degree crankshaft. So now we're looking at what the power pulses to the rear wheel would look like on a 270 degree crankshaft twin cylinder engine. For example, Honda Africa Twin, perfect example of why they use the 270 because of the power delivery. That's basically why. A 270 crank isn't as smooth as a 180 degree crank engine, but they're moving those power pulses closer together, so you get more of a torque burst here and more of an opportunity between the power pulses to regain or maintain traction. When I was illustrating how some of the, on a twin cylinder motorcycle, the power pulses are going to be spread out 4 times as much, and then I illustrated the 270 degree crank pushes them farther together, you think to yourself, well, can you get those power pulses to be all the way together? Companies experimented in the 60s with twin cylinder engine designs where both cylinders fired at the same time. These were referred to as a twingle because it was a twin cylinder that acted like a single cylinder because they both fired at the same time, producing a much bigger power pulse, twice the size, every time the engine fired and transmitted power to the rear wheel. The problem was the power was so great, transmission technology at the time and clutch tech of the time was lacking, and the power was overcoming other mechanical properties within the motorcycle and causing failure. All right, so here I'm illustrating what a 4-cylinder power pulse pattern might look like. Probably the biggest reason why 4 cylinders are never used in off-road bikes is because the power pulses to the rear wheel are so frequent, it's very difficult to maintain traction. Has anybody here ridden a 4-stroke 4-cylinder motorcycle off-road? Anybody? Yeah, you in the back there. Oh, Daryl from The Walking Dead. Your second bike from that show was a 4-cylinder.
This bike, I think, expresses a lot about really, truly what Norman is as a human being and what Daryl is as a character.
Yeah, let's go ride these, like right now.
And I'd be willing to bet that Daryl in that show, when he was running down the road, running from zombies, had a tough time maintaining traction around corners because there's just more opportunity for the tire to break traction. And in reality, the way the engine is geared to the rear wheel, these dots would be pretty much on top of each other. And with an electric motor where there are no power pulses, the whole thing is just power. The whole thing would just be all white, just one white line. That's why electric bikes have a difficult time at slow speeds maintaining or hunting for traction. At higher speeds, this doesn't really matter. Anytime you're in second gear with a regular ICE engine, or if you're moving at over 15, 20 miles an hour on an electric motorcycle, this doesn't really factor in. This has nothing to do with it. It still might have a tiny fraction of a part, but not really. It's the difference is negligible. So you'd ask me, well, Eric, yeah, but this is a 4-stroke engine. 2-stroke engines fire every time the piston reaches top dead center in the engine. So wouldn't that cause an issue? Well, no, because 2-stroke engines, 2 reasons, 2 big reasons that I can think of. 2-stroke engines always operate at a slower RPM than a 4-stroke engine. You look at the rev range between, say, a KTM 300 2-stroke and a KTM 250 or even a 450 four-stroke, the rev range of the four-stroke is usually twice as long or twice as much as the two-stroke engine. And also, like when you are on a two-stroke or you dump the clutch or slip the clutch to get going, your revs are usually around 1500, 2000 RPM. Whereas on the four-stroke, your revs are probably going to be closer to 2500, 3000 RPM. So realistically, the two-stroke engine, even though it fires twice as many times, is revving at half the speed to do the same amount of work. So this still holds true with a two-stroke engine. The other major reason that two-strokes have more of an advantage is because the internal engine resistance of a two-stroke is much less. They don't have a valve train and springs to overcome. The compression ratios will probably be close to the same between two-stroke and four-stroke. Four-strokes may be a little bit higher, which may add some resistance. The two-strokes have less internal rotating assemblies. That means on a two-stroke, the engine drag from in this time period, in this distance, the drag or resistance of the engine internally is less on a two-stroke than it is on a four-stroke. Another reason four-stroke engines are easier at slower speeds is because of the RPM range and the power band of a four-stroke or two-stroke engine, and the takeoff RPMs and the clutch, your clutch slipping ability. So with an electric motor, the torque curve of an electric motor is flat, straight across. So you can modulate that power a little bit with the throttle, but not as much as you can with an internal combustion engine. An internal combustion engine power band, if you ever look at a torque curve, it's going to be curved. It's going to start at zero. As the RPMs rise, the power rises, and then eventually you get valve float and the power starts to drop off. So when you're taking off at 2,000 or 3,000 RPMs, that power in the torque curve is still relatively low. Like say you have a 50 horsepower engine, that 50 horsepower is delivered at 8, 9, 10,000 RPM. But if you're taking off at 2,000 or 3,000 RPM, then the power delivery to the rear wheel is only going to be a small fraction of that total horsepower rating. So it's going to be, 10 horsepower probably realistically being delivered, or 10 foot-pounds of torque to each one of these power pulses. Also, with an electric bike, there's no clutch. So you can't modulate. You don't need the clutch because when you come to a stop, the motor comes to a stop with the bike. And obviously, you don't want the motor to come to a stop or to die on an internal combustion engine. You want the engine to continue running, so you pull the clutch in when you come to a stop. And when you get going, you slip the clutch to allow some forward momentum to build of the motorcycle, and then you fully release the clutch and away you go. When you're hunting for traction, you're feathering the clutch and allowing only some of that small amount of power from the engine to be transmitted to the rear wheel and to each one of these power pulses. One other factor that a lot of people mention is tire types and tire compounds. And this has everything to do with sliding versus static friction. When your tire's rolling, at any given moment, the tire is in a state of static friction. It's like if you were to take a snapshot of someone just riding down the road, not doing a burnout, the tire would not be spinning in relationship to the ground. Different tires are made for different scenarios, and different rubber compounds are made for different tires for different scenarios. One of the reasons I use Trials tires on my 250 is because the way the power is delivered from the engine works best with that type of tire, because Trials tires have more surface area on the dirt and the rubber compound is typically softer. The Trials tire, though, has a really poor coefficient of sliding friction. So when you're doing a burnout or you're sliding down a hill with the rear brake locked and you're putting the tire in a state of sliding friction, it doesn't offer much grip. Not nearly as much grip as a true off-road knobby tire. Knobby tires have a really high coefficient of sliding friction and less of a coefficient of static friction compared to the Trials tire. One thing companies have done to compromise between the two is the gummy hybrid tire. The gummy hybrid has a really soft rubber compound design that allows it to grip various terrains much better. So you get some of the benefits of the Trials tire through the compound, and you get some of the benefits of the knobby tire with the knobs offering a higher coefficient of sliding friction. So basically, if you think of the power pulses as being a positive torque input to the rear wheel every so often in time in relation to the wheel turning against the ground. So what are some of the things that an electric motorcycle company or the engineers at that company could try or implement in order to give off-road riders some of the slow speed tractability that we want on the trails? Because these power pulses act as a reverse anti-lock brake system, almost like traction control a little bit. The electric company engineers could try some kind of a traction control mode where it interrupts the power, because on an electric bike, the power to the rear wheel is constant. So these dots won't even be here. It'll just be a fully white line. So if they could find a way to interrupt that, and then maybe you could even dial it in so the interruptions occurred farther apart or closer together, that might give you a significant advantage in trying to find traction off-road at slow speeds.
If they could introduce some kind of a program, a traction control program, to deliver pulses of power to the rear wheel, and it'd be nice if and when they do that, they deliver the power pulses, or they allow the rider to dictate the frequency of the power pulses like you can with a 4-stroke, 2-stroke engine. The 4-stroke, 2-stroke engines, we dictate the frequency of the power pulses to the rear wheel based on the transmission. Here in first gear, the power pulses are a lot more frequent. Second gear, they become less frequent, and so on and so forth. So if they can do that, they'll be a contender. If not, I see electric bikes having a pretty bright future on the road, where this hunt for traction isn't really a concern, because the coefficient of friction on pavement is really high, and it's very difficult to break traction on pavement. That's where an electric bike shines.
The other thing they could try is a clutch. Unfortunately, the way electric motors work, it makes using a clutch with an electric motor really difficult because of the mass of the clutch. Because the way an internal combustion works, the internal combustion engine has momentum, and that allows the clutch to grab, and the momentum helps the engine not stall when you engage the clutch. And an electric motor doesn't have that, so it would be really difficult to make a clutch work with an electric motor. You'd have to really, really rev it up, get the electric motor spinning fast before you could engage the clutch. And then your clutch, there'd be so much slippage before you fully disengage the clutch or fully engage the clutch, that the clutch would probably wear a lot more prematurely than on an internal combustion engine. Anyway, that's my 2 cents on electric bikes and physics and traction. I hope you enjoyed this video. If you did, give it a thumbs up, give it a like, give it a share, subscribe, all the things. Click all the buttons. Do me a favor, and I'll see you next time. Thanks.